Hello students, very good morning. So in the previous class I have told you about surface chemistry, that we have discussed adsorption, desorption, sorption and all these things, and difference between physical adsorption and chemical adsorption. We have gone through that. So right now it is the second portion of that particular topic, that is colloidal solution. Now we will start colloidal solution. This colloidal solution, it is not confined to any form of metal. Anything can exhibit this colloidal. So anything can exhibit this state. As I have written over here colloidal solution, so definitely it is a solution having two or more components here, but basically we consider two components. Generally in case of a solution we are using solute and solvent, and here for solute and solvent different words are there having same significance. I will tell you. So right now suppose I consider some in a beaker, let's see, suppose I am considering three containers. This one is second container and this one is third container, let's say. Is that okay? So third container, suppose this one is first container, second container and is third container. Okay, so in first container just take water. In every container you just take water. Here water plus sand, and in second container this one is water plus milk. Is that okay? The third container you can take water plus sugar. You see here the sand particles do not dissolve in water, and it is clearly visible to naked eye. Is that clear? So due to large size of sand, insolubility of sand in water, so this type of solution is called your suspension. Okay, now here water plus milk, it is not homogeneous at all. This one is heterogeneous and this one is also heterogeneous, not homogeneous at all. Okay, so here water plus milk, this type of solution is known as your example of your colloidal solution. I will tell you whenever we consider the difference in properties of three categories, and water plus sugar, sugar completely dissolved in water, this one is homogeneous. That's why this solution is called as your true solution. Let us consider their properties, how they differ from each other. So very commonly you can see this one is, let's say, suspension, and this one is colloidal solution, and the last one, that is your true solution. You have idea about true solution. Is that clear? So first one, that is nature, particle size. This one is very important, particle size. So from particle size you can predict what type of a solution is this. Particle size in case of suspension, that is greater than 10 to the power 3 angstrom, or you can say 1000 nanometer. Particle size particularly large. In case of sand, you see it is visible to naked eye. So colloidal solution, its particle size lies between 1 nanometer to 10 to the power 3 nanometer, or you can say 10 angstrom to 10 to the power 3 angstrom. The particle size is an intermediate. Okay, so here in case of true solution, you see it completely dissolved, particle size is very small, less than 1 nanometer, or you can say 10 angstrom. This is particle size. Next, nature I have told you just. Nature, the suspension, clearly this is heterogeneous. Copy for colloidal solution, this one also heterogeneous. And true solution, this is homogeneous. Clear? Next, that is visibility. If you visibility consider, so this one is visible through naked eye. Here it is not visible through naked eye, rather than you can use any UV microscope. Okay, possible through microscope. And true solution, it is not visible, not possible through microscope as well as naked eye. Okay, so next we will go through properties of different types, different properties like diffusion. And this diffusion, first of all, this suspension does not diffuse. And here in case of colloidal solution, you can have slow diffusion is very slow diffusion. And next here rapid diffusion, diffuse rapidly. Okay, next filtration. Here it can be filtered through ordinary filter paper. Can be used for filtration of a suspension, and a colloidal solution you can use membrane for this one. Is that clear? True solution completely dissolved particles are there, it cannot be filtered. Okay, next, that is settling, it settle under gravity. It can be settled down under gravity. And colloidal solution under centrifugation. And here true solution, it never settled. So these are the properties, but you just focus over here that colloidal solution means the solute particle size should lie between 1 nanometer to 1000 nanometer. Is that clear? 1 nanometer to 1000 nanometer, this is very important point for colloidal solution. If the particle size lies within this region, then that solution is said to be a colloidal solution. So in case of a solution, we are using solute and solvent. So here also we are using solute. That colloidal solution I can write over here. Colloidal solution, it having two components like your dispersed phase plus dispersed medium. Here this dispersed phase stands for solute and this dispersed medium stands for solvent. Is that okay? That means this one present in excess amount and this one limited amount. Okay, so this is what I called colloidal solution, having particle size lies between 1 nanometer to 10 to the power 3 nanometer. This is the colloidal dimension. This is called colloidal dimension. Okay, so now we will go through if what will be, and somehow your colloidal solutions are also known as salts. These are called salts. Okay, if your dispersion medium is water, then it is called hydrosol you can say. Okay, if it is benzene is taken as your dispersion medium, or you can say as solvent, then it is called benzosols, and in case of alcohol it is called alkosols. Okay, next we will go through their classification. Okay, classification of colloids. Classification of colloids. Classification of colloids. Students, so first classification that was based on your physical states of dispersed phase and dispersion medium. Dispersed phase and dispersion medium. First of all, I need to say over here, both the components, that is a dispersed phase and a dispersed medium, can't be considered as gases, because you know mixture of gases always leads to homogeneous mixture. So you know a colloidal solution is not a homogeneous system, it is a heterogeneous system. Different phases are there. So based upon the physical states, these are the representation of classification, and these are examples are very important. So this is smoke, example of your aerosol, cord cheese, these are jellious substances, and here the physical states are mentioned over here. And remember, gas plus gas is not considered in case of your colloidal solution, because it leads to a homogeneous mixture. That clear? So next we will go through, depending upon the interaction of your dispersed phase with dispersion medium. Again, the classification has been done like this. Colloidal solids are classified into two categories, as that is, one is lyophobic. Phobic means solvent hating nature, lyophobic, and another one is lyophilic. Lyophilic means solvent loving character. Okay, so it is prepared, this lyophobic solution can be prepared through several specialization methods are there. You can prepare it chemically, or we will discuss during the preparation of colloids. And lyophilic solution, since the dispersed phase can easily interact with the dispersion medium, so it can be prepared by simply you can warm it, or you can shake it the solution, and you can easily get this lyophilic salts. And this is irreversible. Suppose you warm the lyophobic solution and the dispersion medium get separated away through evaporation, then the residue remains, that is not regarded as your colloidal salts. That the dimension of residue, the particles dimension, that is not lies between 1 nanometer to 1000 nanometer. That's why this is irreversible, whereas the case is opposite in case of lyophilic. And lyophilics are more stable here due to less interaction of dispersion medium and a dispersed phase. That's why it is less stable. Viscosity and surface tension equal to that of a definitely your dispersion medium, because you know since there is no interaction, so these properties almost remain same to that of a dispersion medium. The case is same case is not in case of lyophilic, since the dispersed phase particles dissolved in a dispersion medium, so it corresponds to low surface tension and more viscous nature is there. Is that clear? So particles generally have no charge in case of lyophilic, whereas your lyophobic colloid particles having some charge. Is that clear? So next we will go further classification, that is, again the next classification, that is depending upon the size of colloidal particles. If you consider the particle size, colloidal particle size, then salts are classified into first one, that is multimolecular, and the next one is macromolecular, and the third one that is associated. This one is very important, associated colloid. Associated colloids. And multimolecular colloid means, see, it is nothing but the aggregation of dispersed phase particles, that can be aggregation of atoms or aggregation of molecules, okay, leading to the multimolecular colloids. Multimolecular colloid means atoms or small molecules get condensed, get aggregated, and giving us the particles having colloidal dimensions, that is 1 nanometer, within 1 nanometer to 1000 nanometer. Is that clear? Next, macromolecular means here particularly molecules having larger size, that is near about 10 to the power 3 nanometer. These are known as macromolecular colloids having large size. Next, that is associated colloid. It is very important to all of you. You see, what do you mean by associated colloid? The colloid in which associated colloid, that is very important, substances whose molecules, associated colloids, associated colloid, the substance whose molecules get aggregated in a solvent, or you can say dispersed medium, DM I am writing over here, dispersed medium, to give particles of colloidal dimension. These are known as associated colloids. So associated colloid means, simplicity I can consider your soap solution. Soap solution is a colloidal solution whenever the concentration of soap is more. That is the example of one associated colloid. How? Because you know, soaps are, in soap the constituent units are higher fatty acids, sodium or potassium salt of higher fatty acids, that is C17H35 COONA. This one is known as sodium stearate. Okay, so this one act as a surfactant. Actually, see, whenever these molecules get dissolved in water, what happens? In water, you see how the aggregation actually occurs. You see, let's say this one is one container, and I am representing these surfactant molecules or sodium stearate like this one, this one, like this one. So this one is your hydrocarbon part or non-polar part, okay, or this one is known as tail, and here this one is polar part, or this one is called head. Is that clear? So you dissolved in water, it is present in soap, you dissolved in water, and water is a polar solvent. You see, so what happens? The aggregate like this, here the head part will be pointing outwards and non-polar part oriented towards the center, like this. Okay, so this one is double bond O minus Na plus, double bond O minus Na plus. These are head portions, particularly O minus Na plus, O minus Na plus, O minus Na plus, O minus Na plus, O minus Na plus. So this aggregation, that is the non-polar head portions are attracted towards the center and while the head portions pointing outwards. Such an aggregation is called micelle formation. Okay, so now they behave as a colloidal particle. So due to such aggregation, what happens? The grease particle that is present in your cloth, that can be trapped through these tail portions, okay, at the center, and it can be separated away from the cloth. That is known as cleansing action of soap, or this one is known as emulsion. This aggregation is known as micelle formation. Okay, so such an aggregation of a surfactant molecules, that is called micelle. That clear? Now, so this is the example of your associated colloid. Next we will proceed through actually how we prepare such colloidal salts. That is preparation of a colloidal salts. In this case, disintegration method means generally particles having dimension more than that of a colloidal dimension. Okay, so here the particle size should be greater than 10 to the power 3 nanometer. So we have to apply this disintegration method so that we can back the dimension of particles into within the region of 1 nanometer to 1000 nanometer. Is that clear? So this method is your disintegration method, and here this method is condensation method. Okay, so here the particle, generally the particle size less than 1 nanometer, we have to increase their dimension up to 1 nanometer to 10 to the power 3 1000 nanometer, and here, but here the case is opposite. Particle size is very large, we have to break it and again back into your colloidal dimension, that is 1 nanometer to 10 to the power 3 nanometer. Okay, so first one, that is Brady arc method, very important. Generally the metal salts, you can say gold salts, platinum salts, okay, and silver salts are prepared by this Brady arc method. Okay, little bit of information I need to provide over here. So very simple method is there. You just take a container like this. Okay, another container filled with water, you can take this one filled with water. This one is water, and take the metal rod whose respective salts you need to prepare over here. Suppose I am considering gold, these are gold rods. Okay, so one is positive terminal, that is anode, and another one is negative terminal, that is cathode. Same, these two are your gold rods, AU rod. Is that clear? So here this region is filled up by your ice. These are filled through ice. Now if high potential voltage is applied through this container, high potential voltage is applied, here you consider water, then an arc is generated over here because you are applying high potential through these gold electrodes. So this arc is generated there, arc is generated. So due to such high potential you are applying over here, there is the liberation of gold vapors. Gold vapors will be liberated here, and if these are vapors, they can go above, so no profit will be there. We can't get gold salt, so we need to condense these vapors. Okay, so for that condensation we have filled here with ice, which decreases the temperature of the system. As a result, these vapors get collapsed or condensed and remain in the water, so that we can easily get your gold salts. And remember, here also some amount of potassium hydroxide is also added, because once this gold vapors get condensed and we are getting gold salts, again they can combine, aggregate to form larger size particles. Okay, so in order to get the colloidal dimension, this KOH, this, suppose this one is your gold salt, AU, this one is your gold salt, then the rule of KOH is it will furnishes OH minus ion, and they can be reside over this surface, they can adsorb at this surface, so that these gold particles becomes stable and they never interact with each other, because negative charge repel, another gold will be there will be also negative charge, so this negative repels to one another, so that we can stabilize the salt. So this is the Bradick arc method, very easy method. And next one, that is peptidization method. Peptidization means here you consider, this peptidization method means you consider water plus freshly prepared precipitate, plus you need an electrolyte over here, plus electrolyte, and you shake this solution, that is called peptidization. You just inject this mixture, water, freshly prepared precipitate and an electrolyte, respective electrolyte, in a test tube. Let's say this one is a glass tube. Here you take water plus freshly prepared precipitate plus respective electrolyte, then shake that test tube, you will get the respective gold sol. How you can prepare like this? Just imagine, for example, let's say freshly prepared, that is silver chloride, I am saying AgCl, freshly prepared precipitate, that is silver chloride, AgCl, water plus AgCl plus an electrolyte I am considering over here, that is, let's say AgNO3. Okay, the electrolyte you consider over here should be a common ion to that of your colloidal sol. Okay, in sol, that is silver plus, and I have to consider AgNO3, the common ion, that is Ag plus. So in AgCl colloid, your Ag plus get adsorbed at the surface, leading to a positively charged colloid over here, Ag plus, Ag plus, Ag plus. Is that clear? So this is called peptidization. Next, here you see chemical methods are, I have written already over here, that is double decomposition, AS2O3, 3H2S, AS2S3 arsenic sulfide salt plus 3 water. Here you see this compound decomposes and this compound decomposes, AS2S, this S belongs from H2S. So this compound breaks, as a result you are getting the respective salt. So this is called your double decomposition. A reduction you can see over here, you have prepared here gold salt, 3AuCl3, 3SnCl2. You can see there is a removal of chlorine over here. So this is a reduction reaction. And oxidation reaction, bromine plus H2S, you see the removal of hydrogen from sulfur, that is called a reduction. Removal of hydrogen from sulfur, that is called a reduction, and you have prepared colloidal salt of sulfur. That clear? Next, hydrolysis FeCl3, interaction with water, then FeOH3 colloidal solution is prepared. If you take over here, in case of oxidation SO2, then liberation of water will be there. Okay, so these are the chemical methods of preparation, or you can say preparation of a colloidal solution. And you remember, these methods are only applicable, that is lyophobic colloids are prepared through these methods, because preparation is difficult in case of there is due to lack of interaction between dispersed phase and dispersed medium particles. That clear? So this is all about the preparation of colloid. Let us discuss. So properties like heterogeneous character, as I have told you, colloidal salts are heterogeneous in nature, different phases, dispersed phase and dispersion medium, two different phases are there. And next is visibility. Visibility, as I have told you, colloidal particles cannot be visible through naked eye. You can use microscopes for their visibility, for the visibility of particles, colloid particles. And next is filterability. Filterability, colloidal particles can pass through ordinary filter paper. They can pass through ordinary filter paper, but cannot pass through cannot pass through parchment membrane, special membrane, parchment membrane. Is that clear? So for purification you can use this parchment membrane. For the purification of colloidal salts you can use this parchment membrane through which colloidal particles cannot pass. Generally what happens in colloidal solution, there is also some crystalloids dissolved, that is in the true form. True solutions are also there, crystalloids are present along with the colloidal particles. Then what you have to do, you just that is called dialysis. You just carry a container whose surfaces walls are made through parchment membrane and you allow to pass the water through this membrane. Okay, so what happens inside this membrane, your colloidal particles, colloidal solution is there, salts is there. So by passing water, what happens, the crystalloids which are dissolved completely, they can pass away through the current of water. But the colloidal particles, since the parchment membrane never allow to pass through them, their dimensions are that their dimensions prevent, due to their large dimensions of colloidal particles, they can't pass through parchment membrane. As a result, you can easily isolate that colloid sol through that process is known as dialysis. Okay, so here surface tension viscosity, as I have told you, in case of lyophobic it always remains nearly same to that of a dispersion medium, but in case of lyophilic solution viscosity increases and surface tension decreases. Colligative property, colligate definitely if you consider same dispersed phase particles. So here this is I am considering a true solution, dispersed phase remains same. Here also dispersed phase, and this one is true solution, and here this one is colloidal solution. You know the particle size in true solution is very micro. Okay, whereas in colloidal system such particles aggregate to form limited amount of particles are there. Suppose there is 100 dispersed particles are present in true solution, the aggregate may be here 50 particles are there in colloidal salts. Okay, so as you know, all the colligative properties that you have faced in your liquid state, elevation in boiling point, depression in freezing point, relative lowering in vapor pressure, all these quantities in case of depends upon number of particles. So here you see the number of particles is less than compared to true solution. So definitely its boiling point is more than that of this one. Is that clear? So all these properties depends upon particles. Here due to less number of particles over here, the boiling point becomes less than that of a true solutions. Likewise, next, that is very important, Tyndall effect. That is the special characteristics of a colloidal solution, which due to this properties you can differentiate the other forms. That is true solution can be distinguished from this solution. That important property, that is Tyndall effect. So this Tyndall effect and correlation, these are optical properties. You see, suppose you consider this one. This one is a true solution, that is I can say water plus sugar. Okay, another container, this one simply plain water, distilled water, plain distilled water. If I pass light over here, then what we will see here, this middle portion there is no light, and after here it can pass like this. Is that clear? So in case of distilled water, same case arises over here. But if in a container, suppose I am considering a container, this one having distilled water plus milk, so definitely milk, it gives you a colloidal solution. If I pass light through this solution, then you will able to see that they can penetrate through the solution like this, and again get pass away this here. But this case is not arising in this case. How it is possible? And you have some idea, I am telling you, suppose a dark room is there and certain hole is created at the floor, you can say, at the top certain hole is created, then sunlight get enter through this hole to this dark room. Then if you have an idea, this is the practical life we have faced, then that light in a dark room, you see some dust particles are traveling with that light. Okay, that is exactly what I need to say, Tyndall effect. So in this case here, what happens? Now the particle size is comparatively large. These colloidal particles, this incident light get scattered by these particles. The light will get scattered after striking these colloidal particles. That's why we can able to see the penetration of such light radiation through this solution. That is possible only in case of colloidal salts. Okay, so this is called Tyndall effect, the scattering of light over the colloidal particles. That is not in the case of true solution or pure solvent, you can say over here, due to lack size of very minute size of particles. So homogeneous, these are homogeneous, and this one is heterogeneous. So the special property of a colloidal solution. And you see these particles like that of gas molecules, they are traveling here and there, they are traveling with respect to all direction and also striking among themselves. So they move like in this manner, like this manner. So this type of motion of colloidal particles is called Brownian motion. This is called Brownian motion. And color property, very easy. If you see in different directions, then different color will be there. Okay, how it is possible? Because you know the visible light whenever fall over these particles, Sol particles, colloidal particles, then scattering of light will be there. So due to such transmitted light having different wavelengths, okay, so they appear in different colors. Is that clear? So these are the important properties of your colloids. Now let us discuss why certain colloidal particles are charged particles, mainly lyophobic salts having charge. Why? You see, if I consider need to prepare, this is, let's say, AgNO3, silver nitrate I am writing over here, plus let this one is Ki, potassium iodide. This one is excess means this one is your dispersed medium and this one is dispersed phase. Dispersed phase and this one is your dispersed medium because of excess. And the sol I am getting over here, that is AgI. This one is sol plus KNO3. That clear? So you see this AgI sol can be stabilized through the adsorption of which ion? An ion which is common to that of a dispersion medium, because it is present in excess amount. So the maximum ions that will be present over here, that is I minus. This one is common to this colloidal particle. So what happens in this, at the surface, this iodide ions are get collected over here and making this colloidal particle as negative charge. Negative charge. Clear? So these are negative charge. Then what happens? What about this potassium ions? K plus are also there. They will remain intact just within this electric field. Plus, 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 positive, 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 positive. These are potassium ions. Okay, like this. And this negative ion layer, this is fixed layer which protect that AgI, which is called fixed layer, and this positive ions, these are called your movable layer, or you can say this is a diffused layer. Diffused layer. So due to this charge separation, there exists a potential that is called, this positive negative charge are there. So there exists a potential difference that is called zeta potential. That is called zeta potential. zeta potential. And another experiment can be explained over here, that is called electrophoresis or cataphoresis. Electrophoresis or cataphoresis. Let me vanish this one. That is called your electrophoresis or cataphoresis. Electrophoresis or cataphoresis. So very simple experiment is there. You just consider a U-shaped tube over here. Within this tube you just take two electrodes over here. One is positive, that is anode, another one is negative, that is your cathode. Okay, so here just only take water solutions, water as your dispersion medium. Then you need to provide colloidal solutions over here. Then a reservoir is connected over here. Which provides here in this container. Suppose your solid there. Okay, so whenever electric field is applied, then you see, suppose this one is negatively charged colloid, then it is move towards negatively charged colloid, move towards anode. So let's say this one is your anode, positively charged, and this one is your cathode, negatively charged cathode. Then what happens? These particles will move towards anode and get collected there. Okay, get collected there. So here so here can be like this, negative, negative, negative. So it indicates the particles are negatively charged colloids. Okay, that can be known. The water level from this end go on decreasing, and here water level go on increasing. From this it is clear that the colloidal particles having negatively charged, because they are migrated towards anode. This is called cataphoresis or electrophoresis. Clear? Next, very important, that is called your, suppose a colloidal solution is there. This one, I am considering this one as negatively charged colloid. A negatively charged colloid is there. Okay, so if I add an ion, any positive ion I need, suppose add over in this colloidal solution, then what happens? This positive charge will be here, and this colloidal particles, since having negative charge, they can aggregate surrounding this positive charge. So the ion that I have added over here, that is called flocculation ion, flocculating ion. Okay, so flocculating ion, what is the role of flocculating ion? It is responsible for the aggregation of colloidal particles, or you can say for the coagulation of colloidal particles. Is that clear? More the magnitude of valency of this flocculating ion, more will be coagulation. You just remember over here, more the valency of flocculating ion added, more will be the aggregation or coagulation. So if I consider ions like Al3+, barium 2+, and sodium plus. Here you see the valency of 3 positive, 2 positive. These are the order of their flocculating tendency. Okay. So next, that is, and this was given by your, this is called Hardy-Schulze rule. Hardy-Schulze rule. Okay, so more the magnitude of a positive charge, more the valency, more will be coagulation or aggregation. Okay, so next, that is we need to discuss over here, very important, that is gold number. Gold number, that is your protection of colloids or gold number. Since protection of colloid, you know, the lyophobic salts are unstable, so in order to protect lyophobic salts we need protective agent, that is lyophilic salt. So here, that is gold number, I can define over here, gold number, the number of milligrams of protective colloid, that is your lyophilic colloid, protective colloid required to prevent the coagulation of coagulation of 10 ml lyophobic salt containing 1 ml of 10% sodium chloride solution as your electrolyte, sodium chloride solution. Suppose this one is a container, you need to find out the gold number, need to protect your lyophobic solution. You just take over here 10 ml of lyophobic salt plus containing 1 ml of 10% NaCl as your electrolyte. Then gold number means how many milligrams of lyophilic salt you are adding in this solution for the prevention of coagulation of 10 ml of lyophobic solution containing this much amount of NaCl, that is called gold number. So I can define over here, very simple, gold number, that is equal to number of milligrams of lyophilic salt divided by volume of solution into 10. Is that clear? So now it can be predicted if suppose I am giving you an example, that is, now you see this question, that is on addition of 1 ml of 10% NaCl solution, this is compulsory, no need to 10 ml of gold salt. Okay, this one is lyophobic, this gold salt is your lyophobic one, in presence of 0.25 gram of starch. This one is a lyophilic starch solution, 0.25 gram of starch. The coagulation is just prevented. What is the gold number? That means everything condition is okay. Then you have to calculate only the number of milligram of starch. So you just convert this 0.25 gram into milligram. So answer will be your 0.25 into 10 to the power 3. That will be equal to 250 milligram. So this one is your gold number. Okay, and you just remember, suppose you need a certain amount of lyophilic solution to prevent the coagulation of a 10 ml of a lyophobic one. Okay, so what is your expectation? If gold number is more, then protecting power will be less. Suppose you add very little amount of lyophilic substance and that is enough to prevent the coagulation, that means it is more protecting power. Okay, so relation will be like this, your gold number is inversely related to the protecting power, protecting power, very important, gold number is inversely related to the protecting power. Okay. So with this I finish your chapter, that is surface chemistry. Hopefully you get it. Thank you for your kind attention. Okay.